Last video we talked about derivative, and this time we're going to be talking about integral. An integral is just the area below a curve. Let's say we wanted to find the integral of this curve here. Well, what would obviously come to mind was just give me the formula and then I'll plug in the numbers. For example, a square, I just need to multiply this side by this side. But there's no formula for this weird parabola. Like, we have formulas for triangles, circles, everything, but not for this parabola. So let's try to approximate it a little bit. Let's try to fill it up with a bunch of rectangles that we do know the area of, and fill this parabola up. Now, it's sort of close, but it's not quite there. It still can do better. So instead, let's make them even thinner. Now this is an even better approximation, but it's still not quite there. So what if we made this so small, each little sliver, that its width was infinitely small, and the addition of all these little slivers from here to here would actually be the total area? Well, the width would be called dx. You might remember that from derivative. So dx times its function y is going to be the area of this little sliver, y times dx. And basically what integrating is just adding all the little dx's from any area you choose inside a curve. So we wanted to go from a to b. Then the integral would be the integral from x equals a to x equals b. And by the way, this little s thing is the sign for an integral. It just means adding up all the little dx's. Y times dx. Now you might notice here that in a way, integral is the inverse operation of derivative. It cancels derivative. And that's just because if we have the example dv over dt, this would be the acceleration of something. The integral of dv dt times dt, because we need to multiply by dt. dv dt is y, dt is x. The dt's would cancel, and we're left with the integral of dv. And the integral of dv just adds all the little dv's up, so we're left with the total v. Okay, so with that out of the way, let's move to an example that will be helpful for when we derive the rocket equation in a later video in my rocket series. So here we have a curve, and the function of x is 1 over x. So y equals 1 over x. So let's try to integrate this curve from x equals 5 to x equals 10. So that would just look like the integral of x equals 5 to x equals 10, 1 over x dx. Now there's a solution to this integral that allows us to add up all these infinite little dx's. And that's, if we look on this integration table, that's the natural logarithm of x. So this integral equals the natural logarithm of x from 5 to 10. And we can just figure this out by doing the natural log of 10 minus the natural log of 5. So the natural log of 10 is 2.302, and the natural log of 5 is 1.609. So if we subtract these two, we get 0.693. Now we don't just have to do it this way. There's a rule for logarithms that the logarithm of x from something to something would be the natural logarithm of 10, in this case, over 5. And the natural logarithm of 10 over 5 is the same thing as the natural logarithm of 2. And the natural logarithm of 2 is 0.693. So, since we already did this before, that proves that this works. And I'm just doing it this way because when I do a video about the rocket equation, in a later video in my rocket series, when we simplify the equation, it will end up looking like this. So this here is the area under this curve from 5 to 10. So this was a short video about integrals, and hopefully it helped you understand them a little better, and will help you understand them when we derive the rocket equation in a later video in my rocket series. So thanks for watching, and please consider seeing any other videos on my channel, and I highly recommend the rocket series that I'm currently